The content of Chapter 2 is pretty straightforward, but there were a couple of things that I wanted to point out and clarify. The first of which is the approach that the book takes to vectors in general. And this is pretty standard, but for the most part the book approaches it in that a vector is a directed line segment, and everything is derived from that. But that is not the only approach. It's actually also possible to think of vectors as ordered list of coordinates, and if you watch the opening video, the introductory video that I created, I approached it from that particular perspective. Either way is a fine perspective. I would say it's probably more common to think in terms of directed line segments. That's the more standard approach, but I actually personally like it better to think in terms of these ordered lists of coordinates. And I just wanted to give you a little bit of perspective on that. So the scalar product is a great example of this. The book defines the scalar product u dot v as the length of u times the length of v times the cosine of the angle between them. And then from that, it takes this definition here, and from that it derives this way of calculating the sum by taking the product of corresponding parts and then adding those up. So the x-coordinate of one times the x-coordinate of the other plus the y-coordinate of one times the y-coordinate of the other. That's what this means right here and here. On the other hand, however, you could start from this definition. You could say, what does it mean to have the dot product? We could say, what does the dot product mean? Well, it just means to take the corresponding coordinates, multiply them together, and then find the sum. If we start from there, you can, in just the same way, derive this formula for the scalar product of two vectors. So it's not really that important, but it is a subtle distinction, and the book takes a decidedly geometric approach. And when you're approaching these problems, you do not have to approach them from that geometric perspective like the book does. It's just as valid, and I contend in many ways it's better to think of it this way. That's just something to keep in mind as we go forward. The other thing that I wanted to discuss, or to clarify for this chapter, was this particular figure and the statement that went along with it. Study the following picture until you believe that the dot product is distributive for three vectors u, v, and w. And I just don't think that this is a terribly clear picture, so I wanted to try and clear it up for you just a little bit. So I took the liberty of adding some color and some arrows to hopefully at least start us off in the right direction. So let's take a look at this picture. The first thing to note is from the previous, or from earlier in the textbook, it discusses the idea of the projection of one vector on another. If I have one vector here and another vector there, dropping a line straight down. So if this vector is v, then just by trigonometry, and this is the angle theta, then this length right here, this side right here, is just v times the cosine of theta. So that one you should be able to convince yourself of with just a little bit of trigonometry. Okay, so the important thing though here is that v cosine theta is not the dot product of u and v. If this is u, right, u dot v is length of u, length of v, cosine theta. Now here we have this right here, we have v cosine theta, which is what we're referring to up here, okay? But that's not the length of that little segment. It's not the length of this segment because of this extra little u-turn. So if u happens to be 1, and that's what they point out, if u happens to be 1, then this holds true that this is the length of that segment. Alright, so if we take this back to, if we take this over to this picture, that's the first mystery as to why the authors wrote this sort of cryptic u divided by the absolute value of u. Well, that means that this vector right here, this green vector, has length 1. And that means that these the rules that we had over here apply. Okay, so that's the first thing to note. So then we want to see that this right here, that, well, if we look at v plus w, right here, this segment is the projection of that onto our unit vector. Okay? That means that this segment right here is v plus w, sorry, the magnitude of v plus w times cosine theta. Along with that, we also have that this vector here, if we project this vector onto this, we have this portion here, right? So let's label that. That portion is v cosine of theta, is right here, right? And then the last portion, this one is the one that's a little tricky. If we take, if we add another vector here, or not add another vector, but if we think about taking this vector and moving it over right here, and actually we could just as soon take it in there, because remember a vector refers only to a family of vectors, not to any one specific representative. So we could project it here because we're moving it, because it's parallel the whole time, the angles all stay the same. But let's talk about it here. If I take the vector there and I project down, then this portion right here is u cosine theta. But by similar triangles, if I just take that all and slide it down here, I get that this actually corresponds with this portion. So we have v cosine theta. Oh, these are different thetas. I should note, but that's not important. So let's call this theta 1, this theta 2, and this theta 3. Sorry about that. We have here though that the v cosine theta 1 plus u cosine theta 2 is equal to, I'm sorry, that's a w. I made another mistake here. I apologize. W, and this should also be a w. W cosine theta 2. Okay. V cosine theta 1 plus w cosine theta 2 is equal to, sorry, magnitudes there, the length of v plus w cosine of theta 3. Okay. So now let's take a second and look at that. Alright, so we have our little statement that we got from the graph, and the thing to remember is that the magnitude of our other vector u over magnitude of u, the magnitude of that is just equal to 1. So we can add that in wherever we like in here without changing anything. So we can say that the magnitude of u over magnitude of u, v cosine theta 1 plus u over u, these should all have little vector hats, because they're all vectors. W cosine theta 2 is equal to u over u v plus w cosine theta 3. Okay, now we see that this and this and this, each one of those is a dot product, is a result of a dot product, and the dot product is u over the magnitude of u dot v plus u over the magnitude of u dot w is equal to u over the magnitude of u dot the sum v plus w. And that's our distributive property.